Back in the day, forging a crankshaft was backbreaking work that took a crew of skilled craftsmen hours to complete. Today, we're witnessing something extraordinary at Karl Diedrichs in Germany, where tradition meets cutting-edge technology. What you're seeing here is a massive crankshaft blank being heated to 300 degrees Fahrenheit until it glows like the sun. This isn't just any crankshaft. It's destined for marine engines that power ocean-going vessels. The real magic happens with these twin hydraulic forging presses, each capable of delivering 10,000 tons of force. Watch as the first press shapes the rough form, while the second performs precision strikes that compress the steel's grain structure, making it incredibly strong. The computer-controlled system monitors temperature and pressure in real time, ensuring each blow lands exactly where needed. These crankshafts will run for decades without failure, a testament to German engineering precision that reminds us of the great manufacturing era America once led. Remember when gears were cut one tooth at a time on old mechanical machines? Those were the days when a master machinist's skill determined quality. Well, folks, what we're about to see represents a quantum leap in gear manufacturing technology. This is the Gleason Phoenix 2, cutting bevel gears using their revolutionary up-gear technology. Bevel gears are those angled gears you'd find in the rear differential of classic American pickup trucks. Remember those sturdy Chevy and Ford rear ends that just wouldn't quit? Same principle, but now we're making them with space-age precision. The process starts with a forged steel blank, already heat-treated to about 60 Rockwell hardness. That's harder than most drill bits. The workpiece is mounted on a precision spindle that positions it within 0.010 of an inch. Now here's where it gets fascinating. Instead of using traditional cutting tools, this machine employs a generating process. The cutting head spins at 1/500 RPM, while simultaneously moving through multiple axes, essentially generating the gear teeth by removing material in a continuous, flowing motion. The upgear technology uses a stick blade cutter design that Gleason pioneered. These carbide-tipped blades can cut through hardened steel like butter, and they're arranged in a way that distributes cutting forces evenly, reducing vibration and extending tool life dramatically. Back in the 1950s, you'd need to change cutting tools every few hundred gears. Today's carbide inserts can produce 5,000 gears before replacement. Watch how the coolant floods the cutting zone. That's not just water. It's a specially formulated synthetic oil that cools, lubricates, and washes away chips simultaneously. Temperature control is critical, because even a 5-degree variation can affect the gear's final dimensions. The machine's CNC brain calculates thousands of positioning commands per second, adjusting for tool wear, thermal expansion, and even the slight deflection of the machine's structure under cutting forces. The result? Gears with tooth contact patterns so precise they'll run quietly for hundreds of thousands of miles. This technology keeps American manufacturing competitive. While we've lost some industries overseas, precision gear cutting remains a specialty where American and European shops still lead the world. It's a reminder that when we invest in technology and training, our workers can compete with anyone. Now here's a manufacturing process that's been around since the 1800s, but you've probably never seen it in action. We're making C-channel steel, that structural steel shaped like the letter C that's been the backbone of American construction for over a century. This roll-forming machine is essentially a series of precisely shaped rollers arranged in sequence, each one bending the steel a little more than the last. The flat steel coil enters at one end, and through a series of 12 forming stations, it gradually transforms into that distinctive C shape. What's remarkable is the precision involved. The steel is moving through at 100 feet per minute. That's faster than you can walk, yet each bend must be exact. The rollers are machined to tolerances of a few thousandths of an inch and arranged at calculated angles to prevent the metal from buckling or twisting. Notice how there's no heating involved. This is called cold forming, and it actually strengthens the steel through a process called work hardening. The crystalline structure of the metal gets compressed and aligned, making the finished channel stronger than the original flat steel. At the end of the line, a flying saw cuts the continuous channel to length without stopping the process. These C-channels will become part of buildings, bridges, and industrial structures across America, carrying on a tradition that built this nation's infrastructure. Here's submerged arc welding on a 20-inch Schedule 80 steel pipe, one of the toughest welds in the business. That blanket of granular flux covers the arc completely, creating a clean, deep penetration weld that's essential for high-pressure applications. This pipe will handle 3,000 psi without breaking a sweat. Now, this is something you don't see every day. Cutting ACME threads on a 70-inch diameter tube. ACME threads are those trapezoidal-shaped threads you'd find on the lead screws of old metal lathes and drill presses. They're designed to handle heavy loads and resist wear, which is why they've been the go-to choice for power transmission since the 1890s. This massive tube is mounted on a horizontal lathe capable of swinging workpieces up to 8 feet in diameter. The thread specification calls for a 15/16 pitch. That means the thread advances 15/16 of an inch per revolution. For context, that's about twice as coarse as the threads on a standard fire hydrant. The cutting tool is a specially ground carbide insert designed specifically for ACME thread geometry. Unlike standard V-threads, ACME threads have a 29-degree included angle and a flat crest, which requires multiple passes to achieve the correct form. The machinist will make roughing passes first, removing most of the material, then finish passes that bring the thread to its final dimension of plus or minus 5/1000ths of an inch. Watch the steady stream of cutting fluid. At this diameter, the cutting speed at the surface is about 150 feet per minute, generating significant heat. The tube is rotating at just 8 RPM, but don't let that slow speed fool you. The cutting forces are enormous, and the machine's headstock bearings must be absolutely rigid to prevent chatter. Threading this size component requires old-school craftsmanship combined with modern CNC controls. The operator manually set up the job, indicated the tube to ensure it runs true, and programmed the thread parameters. This tube will likely become part of a massive screw jack or lifting system used in heavy industrial applications, perhaps adjusting the elevation of a steel mill's roller tables or positioning components in a shipyard. It's precision engineering on a monumental scale. Watch precision in motion as this Tubotron 120 CNC tube bender tackles 4.5-inch stainless steel tubing. This German-made machine represents the pinnacle of tube bending technology, and it's solving one of metalworking's trickiest challenges: bending thin-wall stainless without collapsing, wrinkling, or flattening the tube. We're working with 114.3 millimeters diameter tube with 3.5 millimeters wall thickness. That's thin enough that without proper support, it would collapse like a soda straw if you tried bending it. The secret is the mandrel system. Inside the tube, a segmented steel mandrel supports the inner wall exactly at the bend point, preventing collapse while allowing the metal to flow smoothly around the curve. The machine's CNC brain controls 7 axes simultaneously: tube rotation, carriage position, bend arm angle, mandrel position, wiper die pressure, clamp force, and booster assist. Each parameter is calculated based on the material properties, bend radius, and wall thickness. Notice the precision tooling. The bend die is mirror polished to prevent scratching the stainless surface, and the pressure die applies exactly the right clamping force. Too little and the tube slips. too much, and you get marking. This tube will become part of a processing system in a pharmaceutical or food plant, where stainless steel's corrosion resistance and cleanability are essential.